Hello, the research I'm presenting is titled Deep Transfer Learning Through Selective Joint Fine-Tuning. It's a stack of several different machine learning methods, and so what I'd like to do is build up a high-level understanding of what's going on in this research, one chunk at a time. So talk about the transfer learning, fine-tuning, what joint fine-tuning is, and finally build this all into something that maybe makes sense. So the first thing I want to talk about is what transfer learning is. Transfer learning is a specialized area of research in the machine learning field that is concerned with preserving learned features from some source task and moving it over to a target task. So for example, if you have an image recognition network and you've trained it to do classification on several different species of birds, and you have some belief that maybe there are features that this network has learned that will also be useful for the recognition of different species of fish. You could use one of several different transfer learning methods to preserve those learned features that will work in this new target domain. The next sort of building block for this algorithm that I'd like to talk about is fine-tuning. Fine-tuning is an early method, or perhaps the first method of transfer learning, and at a pretty natural starting point. So what you do is, if you imagine that you've trained this network for some image recognition task, you would freeze these intermediate layers and allow typically these output layers to train for this new target task. So you preserve some of the learned features here and allow it to adjust for this new task with only part of the network. An issue with this method is that it has catastrophic forgetting. So there's nothing that constrains the network to continue to be able to predict on its original learned task. It just sort of moves on and only cares about optimizing for the new target task. So now joint fine-tuning is an approach that tries to remedy this catastrophic forgetting effect in the instance that you would like to be able to predict on your source domain as well as in the target domain. So what you would do here is, normally implemented in batches, you would pass through data from your source domain and train, and then data from your target domain and train using some intermediate shared layers and some task-specific output layers. So now that we've covered joint fine-tuning, we can cover selective joint fine-tuning. And so the selective part is mostly the contribution of this research, and what they're doing is kind of this left-hand side of the slide. And what this is they have a source domain, and you can see there's things like dogs, lizards, tools, so forth, and then a target domain, which is different species of flowers. And the idea here is that, well, maybe there's some data in this source domain, particularly if this target domain is kind of data deprived and there aren't enough examples to train a good classifier. Maybe there's some data in the source domain that we can identify that will be useful to train with and perhaps give us some better performance. And the way that the authors propose identifying useful data from the source domain is to use this k-nearest neighbors algorithm in a shallow feature space of a trained convolutional neural network. So what that means is, if you have an image recognition network, the early layers have things like edge detectors and sort of these low-level features that are useful, based on the distribution of the data that you're dealing with. So if we find near neighbors in this low-level feature space, maybe we're getting source data that has useful features in it that we can augment our data set. And this slide sort of explains how the k-nearest neighbors algorithm works. So very briefly, if your data point in question is this star here, and you say our neighborhood is size 3, we would assign the star to class B because more of our neighbors are class B. If we were in class, if we had a neighborhood of 6, we'd assign to class A because there are more neighbors in class A. So this neighborhood hyperparameter will affect the size of the neighbors we're choosing here. But this is sort of what we're seeing, is that we have these target domain data in here, and then we're finding source domain neighbors that we're going to add to our data set when we train our network. So these are some examples of data that it was able to identify in that low-level feature space. So here we have from our source domain, and here we have near neighbors that we found. So this is the nearest, the 10th, the 20th, right? Yeah, 30th, 40th, so forth. And so you can see, okay, nearest neighbor, we're finding flowers. This one actually had the same image in it. Maybe the colors in this one are all similar, although the items aren't, or the content of the image isn't very similar. We're seeing, you know, other open spaces, tables, long horizontal lines. Particularly the lines and things like this would be things that would be picked up in the low-level feature space. And finally, here are the different models that they trained. So we have a number of comparison models, and as well as their proposed models here. We see that theirs have the highest accuracy on the tasks that they presented it with. We see that fine-tuning does help, as opposed to just training from scratch, which did not do very well. Selective joint training from scratch did better. So we can see that in general, kind of stacking these methods are squeezing out a little bit of additional performance, and finally theirs seem to do the best here. So hopefully some of that made sense. There was a lot going on with this paper and not a lot of time to explain it, but hopefully you learned something from that.